Physics 2212, Lab 4, Circuits and Capacitors. The purpose of this lab was to predict circuit behavior and conduct experiments to confirm or deny the hypothesis. We then examined capacitor and resistor behavior. We did this by using a circuit simulator as well as basic physics concepts to gather data and observe circuit elements. From this, we were able to determine that the potential difference across the circuit equals 0 and that RC equals 6.61 seconds for this setup. Through this lab, I'm first going to go over the main concepts and then part 1 and 2 of the lab, as well as the discussion question and conclusion. The main physics concept used in this lab included knowing general knowledge of capacitor and resistor behavior, as well as energy conservation, which included the loop rule, which states that the sum of the potential difference in a complete loop equals 0, as well as knowing the node rule, which states that the current entering an intersection equals the current leaving. Lastly, it was important to know Ohm's law, which states that voltage equals current times resistance. For part 1 of the experiment, we constructed a simple series circuit consisting of two 1.5 volt batteries, two resistors, and two ammeters, and predicted the currents that would be measured on the two ammeters. We used Ohm's law, which stated that V equals IR to determine that the I's, I1 and I2 would both equal 0.02 amps. After setting up this circuit within the CCK simulator, I determined that my prediction was correct and that the ammeters read 0.02 amps. We then inserted the connection backwards and determined that the current showed no change. Lastly, we replaced the ammeter with a voltmeter and then read the voltmeter to be 3.0 volts, and this was because there was a drop of 3 volts by doing this change, and the ammeter was equal to 0 amps because it was now an open circuit. Next, within part 1, we calculated the total potential difference across the entire circuit by calculating the potential difference across multiple parts of the circuit and then adding it up. And as you can see, going around the circuit and adding it up, we determined the potential difference to be equal to 0. Here's a graph that goes through each position as before, and as you can see, when you go through the battery, the potential increases by 1.5 volts per battery. And then as you go on through the graph, you can see that it decreases when it gets to the 47 ohm resistor and decreases further to 0 when it goes through the 100 ohm resistor. Some additional questions and observations I noted for part 1 was that the ammeter reading does not alter with the addition of a voltmeter because the ammeter reading is dependent of the resistor and not the voltmeter, as the voltmeter has infinite resistance. Then, if we were to connect the voltmeter across 100 ohm resistor again and note the ammeter reading, the ammeter would continue to read 0.02 amps. And then if we were to replace the voltmeter with the ammeter in parallel with the 100 ohm resistor, what would happen to the current through the other ammeter would be that the current would take the path of the least resistance and then read 0.07 amps. Lastly, for part 1, I did resistance calculations, and using the formula that resistance equals delta V divided by I determined that for the 47 ohm resistor, using my data, it would be about 47.95 ohms. For the 100 ohm resistor, equal to 102.05 ohms. For the wire, the resistance would be 0 ohms, as well as for the ammeter, it would be equal to 0 ohms. For part 2, we did RC calculations, and we did this by setting up a circuit with either a 10 ohm bulb or a 20 ohm bulb and use a 9 volt battery and a 200 capacitor. For this procedure, we charged the capacitor and we observed that as the capacitor charged, the bulb dimmed and the current moved slower as the capacitor charged, and also once it was charged, the light no longer glowed. For discharging the capacitor, we saw that the current reversed in the circuit due to this new charge orientation, and as the capacitor discharged, the light dimmed, and once the capacitor was fully discharged, the light no longer glowed. We used the same procedure for both the 10 ohm bulb and the 20 ohm bulb, and you can see the difference in the time it took to charge and time it took to discharge for both of them. For the 10 ohm bulb, it took about 10.2 seconds to charge and 10.4 seconds to discharge, and then 19.8 seconds for the 20 ohm to charge and 20 seconds for it to discharge. It makes sense that since the resistance is twice for the 20 ohm, that the time it takes would also be twice for both charging and discharging. Moving on, we then conducted time-dependent voltage across the discharging capacitor calculations by setting up the circuit with the CCK 9 volt battery and a 200 capacitor and a 30 ohm light bulb, and we measured the voltage across the capacitor with the voltmeter. We set the capacitor discharging and plotted 20 seconds worth of voltage versus time on a natural log of V divided by delta V naught versus T plot. For the results, I used the equation for the straight line given on the graph, and knowing that the slope of the line is equal to -1 divided by RC, I determined that RC was equal to 6.61 seconds. This RC value was expected to be 6 seconds, so the value I determined was very close. For the discussion questions, I determined that if we use an actual ammeter, the values given for the current will be lower because the resistance will be greater since the simulation assumes an ideal situation, and if we use a real battery to charge a real capacitor with no resistor in the circuit, our ideal model would predict the capacitor to reach full charge instantly, but in real life the capacitor would not reach a full charge because in real life resistance still exists throughout. Conclusion, using the circuit simulator for Lab 4 gave us a good idea of what this situation would look like in real life, and even though not completely accurate, it helped us get the conclusions that we came to of a potential difference equal to 0 and an RC of 6.6 seconds.